In this video, we're going to look at the topics from Lecture 3 in class. We'll review CFA models, including model modifications and model residuals and parceling. So the first thing I'm going to do is load packages I might need. We'll need lavaan to fit SEM models. We're going to use the PSYC package for reliability and EFA, and SEM plot for creating some plots of our models. We'll read in our data. Our data are in a file called lec3.cfa.csv. So the data, just to look at the data, if we want to look at the data, we have, so here we go. We have 6 variables: great, cheerful, happy, sad, down, and unhappy, and we have individual scores on them. We can look at a summary of the data as well. These are data I made up, but we'll use it for this. The correlation matrix of the data, just to replicate what we saw in class. We can compute the correlations there. We see the correlations between great, cheerful, and happy are pretty strong. They're all about 0.6. Same for sad, down, and unhappy. And then the correlations between great, cheerful, and happy and sad, down, and unhappy, they're negative and smaller. Just as a reminder, what we're actually going to fit our model to is the covariance matrix. And so the covariance matrix looks like this. The difference is a correlation matrix, we can see up here, is standardized. All the variances have been standardized to be 1. Correlations are on this metric that ranges from -1 to 1. Covariances are unstandardized. We can see their variances take on different value, the variance of the variables. And so that's what we want to use. To get those reliability estimates we saw, we use the alpha function in the PSYC package. We need to give it, the alpha takes a data set or a data frame that is only the variables we want. So here we're going to say dat, the name of our data set. I use brackets for selection. The comma here means we use all the rows, and then we can put in the names of the variables we want: great, cheerful, and happy. To pick those, and we pick those, we compute our alpha. Alpha is 0.84 here. We also get item deleted, other estimates of reliability, standardized alpha, and confidence intervals for alpha. And then, or we can, instead of using the names, we could use the numbers. So columns 4, 5, and 6 in the data are sad, down, and unhappy. If we do that, we can see sad, down, and unhappy. We compute our alpha here is 0.83 for those. To fit in EFA, we're going to use the FA function in the PSYC package. So we'll give the FA function our data set, and this should be a data set with only the variables you want to do your factor analysis on. The number of factors, we want to extract 2 factors, and we're going to use maximum likelihood estimation. Then we can look at those results. There's a lot here, but just to start at the top, we have our factors, this ML2 and ML1. These are the factor loadings, the rotated factor loadings for, we can see here positive affect, high factor loadings for great, cheerful, happy, low ones for sad, down, unhappy, negative affect over here. We've got H2 communalities and uniquenesses. The correlation between the factors is down here with factor correlations of -0.27. There's some information about model fit as well that we could use to compare models and other information. So now we're going to fit our CFA. And so similar to the code we saw earlier, we're going to call this in lecture, we call this mod 5.1. We identify first our latent variable. So positive affect has factor loadings for great, cheerful, and happy. Negative affect, sad, down, and unhappy. And by default, lavaan would include this, but just for clarity, just to be sure, we're going to include a covariance between positive and negative affect. So remember, our model syntax is just a character. It's a single character value. And then we fit our model. We use the CFA function where we say the name of our model, our data set here. If you're using raw data, we say data equals dat, and then std.lv equals true for our latent, to fix the factor variances to 1. And then down here, we're going to say summary fit, and we'll get a summary of the model. Standardize equals true gives us standardized parameters. Fit measures equals true gives us model fit here as well. So if we look at our results, we have our model fit up here, and this matches what we saw before. This model test user model, the test statistic here, this is the chi-square statistic for the model. There's 8 degrees of freedom for that. So there's a difference of 8 between the number of observed and the number of known pieces of information and the number of unknown parameters to estimate. We'll talk more about model fit next week. We can look at factor loadings. And so just as a reminder about factor loadings, when you're sort of evaluating and looking at the model, these are unstandardized estimates here in this estimate. So we've got positive affect loading on great, cheerful, happy. Here are the unstandardized estimates. Negative affect loading on sad, down, and unhappy. Here are the unstandardized estimates. Those estimates have standard errors, z-values, and p-values. I don't look at, report, consider the p-values for these factor loadings because that's not, I'm not interested in. This is just testing, is the factor loading different from 0? That's not something I'm interested in. Instead, I would rely on looking at the magnitude, in particular, looking at the standardized factor loadings under here under std.all to see, are these essentially large? Down here, under covariances, it has positive, tilde, tilde, negative. This is the covariance between positive and negative affect. If we are using a fixed factor method of scale setting, the estimate, the unstandardized estimate, negative 0.307, is the same as the standardized estimate, negative 0.307. Just as a note, there's 2 different standardized values. std.lv standardizes only the latent variables. std.all standardizes all the variables. So this is usually what we want to look at. But in this case, it's exactly the same because we used a fixed factor method of identification. This p-value we might want to know. This is testing, is the correlation between positive and negative affect different from 0? And it is. And then we get estimates of residual variances. We can see the variance of positive and negative affect is fixed to 1. If we wanted to do this with a marker variable method, we could. All we have to do is set std.lv to false. And then we can look at our results here. Model fits the same. Our chi-square is exactly the same. It's 50.627. The standardized estimates are all the same too. If you look at the standardized estimates, however, the unstandardized estimates are not the same, and actually the test statistics aren't the same. So with a fixed factor method of identification, the z statistic for the covariance is negative 7.749. With a marker variable method, it's negative 6.548. So you do need to be careful in testing, in understanding that, using different methods of scale setting will affect that. So now if we want to look at a diagram, again, this is more diagnostic than something I would use in a paper or presentation. We can use the SEMPaths function. We give our fit model, fit 51. If I say est here, it will include, zoom this in and make it bigger. It will include, and they are hard to see there, these tiny little values here. Those are the values of the parameter estimates. Just as a reminder, so this is, again, mostly uses, okay, great, cheerful, and happy, load on positive affect, sad, down, and unhappy. Load on negative affect. Green values are positive, parameters with positive value. A red value is a negative. You can do the same thing, but get standardized parameter estimates instead if you use STD here. And then you can see those are represented there as well. If we're interested in model residuals, well, first thing, we can pull out the covariance matrix, our observed covariance matrix. So this is the covariances amongst our data. This is based on the data. We can use inspect, say fit 51 SAMStat to get sample statistics covariance. We can also get our model implied covariance matrix. If we use fitted.values, this is the model implied covariance matrix. And the difference between these are those model residuals. So if we take every element in the observed and subtract it from the model implied, we get our residuals. As a matter of fact, that's what this bit of code does, is it takes the observed values minus the model implied values. And if we do that, we get our model residuals. Now we can get the same thing as we saw in lecture using the residuals function. See, these are exactly the same. And all these values are the same, but as a reminder, this says raw. These represent differences between covariances, which may not be terribly useful. So instead, we might be interested in correlations. the residuals, if we say type equals core, it puts those in a correlation metric, and this allows us them to be a little more interpretable. In terms of modification indices, we use the function modification indices. And if we run this, this gives us all of our modification indices. As a reminder, the first part here tells you this is the parameter that would be added to the model. So positive affect loading on SAD. The MI column says this is the value of the modification index. Larger values mean a greater declining chi-square, a better fit. EPC is the expected parameter change. Here's the value that we would think the unstandardized parameter would be. And then this SEPC, this is the standardized expected parameter change. So often it's easiest to look in this SEPC all to get to an idea of, and so for example, we could say, well, this is a really large modification index, but it's only going to lead to a factor loading of about 0.17, which is really not that interesting or useful. Another way to think, we could also say, well, down and unhappy, that's another large one. That would lead to a standardized parameter change of negative 1.5, which is impossible. And we'll see that in a second. So just two other notes. If you use the sort period equals true, it will sort them from the largest to the smallest. So if you just want to find what the largest parameter estimates are, up here it's sorted by type of parameter estimate, first factor loadings, then residual variances based on variables. Here it's resorted, it's sorted from largest to smallest. Or we can use minimum value equals, and it will only return modification indices larger than that. So if I only want large modification indices larger than 5, which can be useful with a really large model, you can return those as well. The other thing we can do that I mentioned in class is we can, in the idea of what's a large residual, we can plot out the residuals. So here I can use the stem function to get a stem and leaf plot where I plot the residuals and I pull out this $cove pulls out just the values of the residuals themselves. And this gives me a stem and leaf plot to look, are they approximately normally distributed? Are there values I should be worried about? Now, I do want to note in this, this is pulling them out from, if we look at the results, this is pulling, you can see this 16.66. This is pulling them out twice. So this is it's giving you slightly, everything is doubled up because it's giving you both the top and the bottom half. We could also look at a histogram of our residuals to again see, are there any extreme ones? And that 0.16, that's indicating it might potentially be an issue. So we can add in, we can modify our model based on modification indices. We can add this dual loading. We can add SAD here. We're going to say positive affect loads on great, cheerful, happy, and sad now. And we'll fit that model. If we look at a summary of the model, we can see a couple of things. We can see parameters that have changed. There is this now positive affect loads on SAD. Now again, this is a case where I don't care about the p-value, but I am a little concerned that the standardized factor loading is only about 0.18, which is pretty small, and it's positive, which doesn't make a ton of sense. Again, if I wanted to maybe look at SEMPaths to see, we can see here's that cross loading. It's not very big, but it's there. One question would be, well, how did this change the residuals, the model residuals? So here's the model residuals from my original model. From the new model I fit, again, we might be worried, this residual of 0.166, and these are standardized residuals, goes down to 0.75. The residuals seem to have gone down. The problem is that modification doesn't make a lot of sense, doesn't seem to add a lot. So we might say, okay, well, we're going to add a correlated residual. If you remember, our modification indices, the next largest change was looking at a covariance between down and unhappy. I had the same modification index. So we'll add that in. We'll say positive affect still loads on great, cheerful, happy. Negative affect loads on sad, down, and unhappy. There's this residual covariance. So this is saying after controlling for the effect of negative affect, there's still something left in down and unhappy that allows them to covary. And so you may remember what happens when we do this. We get angry red text. Some estimated variances are negative. And if we look at our model, what we end up with is we see, okay, the variances for both down and unhappy are both negative. Now, negative variances, sometimes they occur. They occur, and they can occur for a couple of reasons. One, your model is misspecified. You're estimating, in this case, our model is under-identified. It doesn't have local identification. There's a problem with it. Sometimes they just happen as a function of sampling, and that's okay. In this case, it seems pretty clear that the change to the model has led to this happening. Multiple variables have negative variance, specifically the two variables that have that residual covariance. And so this tells us our model's misspecified. This isn't a correct model. Again, we could look at our model if we wanted to look at, and we can see here is that residual covariance down there. As a note, you can see the variances here are red. That's negative. They should never be negative. That's a real problem. So we'll fit one more model looking at a correlated residual across factors. So we won't have this issue of local identification, the correlated residual between great and sad. So this is saying after controlling for the influence of positive affect and the influence of negative affect, there's something else about great and sad that covaries. Oops, let's try that once more to make it pretty. And so now we have our factor loadings again. They're relatively unaffected. We have the covariance between the latent variables. It's pretty similar. And then we have this residual covariance here. We can see it's different from 0. The standardized residual covariance is about, so the residual correlation is about 1.8, 1.9. That's not nothing. That's not something we should totally ignore, but it's not gigantic either. And more importantly, it doesn't make sense, right? The question of making model modifications should really be, does this make sense? Is this something that should have been really obvious? In this case, I can't really come up with the real reason why this residual covariance should be there. So this is not, so in this case, it's not a modification I would make. I would end up going back to the original model. Okay, so we're going to move on now to talk about parceling. To move on to talk about example of parceling. So I'm going to read in data. I'm going to call it DAT2. The data set's called lec3.parcel.csv. These data, there are 12 variables in total, 6 indicators of positive affect, great, cheerful, happy, good, glad, and super, 6 indicators of negative affect, sad, down, and unhappy, blue, bad, and terrible. We can see the correlations amongst all of our items. All the positive affect items correlated about 0.6. All the negative affect items correlated about 0.6. This is a very pretty data set, and there's negative correlations across the two sets. So I could fit a model, I'm going to call this model 55, with with 6 indicators of positive affect and 6 indicators of negative affect. And I've gone one step further with this model. I'm going to use lavaan defaults. It still will include latent variances, latent covariances, residual variances. I'm just going to not include them in my syntax. And then fit this model with a fixed factor method of identification. So we can look at a summary of the model. So in this case, model fit is good. The chi-square is 181.196, but other model fit indices are generally pretty good. The factor loadings are all pretty high, 0.75, 0.83, 0.81, 0.77. We can see all the factor loadings. Positive and negative affect, their covariance is negative 0.29. And we see all the residual variances here. If we look at a picture, we can see there are now 6 indicators of positive affect and 6 indicators of negative affect. Finally, we can look for modification indices to find any values over 10, and we can see there are some, so maybe we should include a covariance between blue and terrible. As a reminder, since we have more than 3 indicators of our latent variable, we can use residual covariances within items, or maybe sad and unhappy should have a residual covariance. That's our largest modification index. Great and glad. So now what we're going to do is we're going to parcel. So instead of having 6 indicators of each latent variable, we'll have 3 indicators of each latent variable. So I'm going to create new variables. I'm going to call this P1, P2, and P3. The first P1 is the average of great and glad, P2, cheerful and good, P3, happy and super. So I've got 3 parcels here. Negative affect, I'm going to take the average of terrible and sad, down and blue, and unhappy and bad, 3 negative affect parcels. And then I'll fit a CFA here, where again, I don't need all this stuff at the bottom, it's just in here as a reminder, where I'm going to use positive affect loads on P1, 2, and 3, my 3 parcels, negative affect on N1, 2, and 3, my 3 parcels. And if I fit this model, now we can see a couple of things, a couple of consequences of parceling. Model fit improves. Model chi-square goes down. Other model fit indices will go up generally. Factor loadings get higher, as we talked about in class. The relations amongst the latent variables don't change very much. The latent covariance went from negative 0.2829 to negative 0.28. But we have a much simpler, more parsimonious model, if that's something that's a concern. In truth, if this were my model, the regular model is pretty simple. I wouldn't actually parcel here, but it's a nice sort of simplified example. If we look at our path diagram now, just as a reminder, we went from this 6 indicators per latent variable to a more simplified version of this. And then if we look at modification indices, we can see there are fewer modification indices. There are still some large ones, but some of those other modification indices disappear, because if we put 2 items with a residual covariance in the same parcel, that residual covariance doesn't exist anymore. So just as a reminder, I also mentioned, I think in methods of parceling, this used, I think, radial parceling, kind of an arbitrary parceling scheme. If you want, we can use the semtools package. And so this mod item, we're going to call it pos. We set up a model here with positive and negative affect, each with 3 items. This is going to use random parcel allocation. So this is going to parcel and fit the data 20 times, 20 different ways. We specify parcel names, which can call them V1, 2, 3, 4, 5, and 6. And so V1, 2, and 3 are in case of positive, V4, 5, and 6 for negative affect. We use the parcel allocation function. So we specify the model that we're going to fit with the parcels, the data set, the parcel names that we created, in a model with unparceled. So syntax for a model, you don't have to fit it, but syntax for an unparceled model, number of allocations. This std.lv equals true we'll use the fixed factor method, and then iSeed, this sets a random number seed. So if we do this, it's going to fit the models 20 times, and what we end up getting is we get our parameter estimates, the average, and this SD tells us how much variability is there across parceling scheme in this average estimate. We can see the minimum and the maximum, and across all 20, this %sig, what percentage of these were significantly different from 0? Here they all were. We also get information about model fit. We can see how does model fit change the chi-square, CFI, TLI, RMSEA, these values. What's the range of change? RMSEA ranging from 0.039 to 0.81. That's a pretty large range. That indicates that it's something we might want to consider. If we want to get actual test statistics across them, we need to pool the results. So we first use parcel allocation. I include do fit equals false here. This is going to create 20 data sets, this parcel list. And then I'm going to use the CFA.mi function with my model, my data. This is similar to what we use for multiple imputation, and we'll talk about that in a couple of weeks. We can use this to pool results, get a summary. This warning message is not something we need to worry about, but we can get a summary of results that includes parameter estimates, p-values associated with them. We can see here across all of those that correlation between positive and negative affect, that covariance is estimated to be negative 0.28, which is, the unparceled was negative 0.29. It's very, very similar here. We can use the ANOVA command. This will give us an estimate of our test statistic. FMI tells us about variability across parcels. And then the fit measures function will give us, in a moment maybe, gives us model fit for the model as well across the different estimates. So that's all for CFA and parceling. Thanks for tuning in, and we'll talk about model fit next.